for questions that they got wrong and think they got right. Or let me rephrase that. That did not presume innocence. Open regrading for people who think that the mark they received was not the appropriate mark for the answer they provided. There we go. No judgment. So we're spending a little bit more time here chatting about differences between these four guys. So if I'm checking the schedule, we're moving on from this next class into some radical stuff. We got a lot of buffer time built into the radical stuff, so we'll be able to come back to this. We won't need 2 weeks to talk about radical chemistry, and then the course is over, and God, the exam is only on the 11th. I don't want to think about that. I'm sure you guys don't either. So last class, I left us with this example, and then I'll open the floor to any other questions. I've got a few in the email of some specific examples some people want to see, and I think I want to talk through a couple of those because I think they demonstrate some common confusions and things I need to sort out. Anyways, so you have an example here, and what I'm saying is I'm saying this is not an addition. And I wouldn't have to say that because addition chemistry to the double bond happens really only if there's not a lot of other things you can do with strong acid, because double bonds aren't super nucleophilic. There is another option here. So, any proposals on what we would do in a situation first? We would chart. I don't think I understand, Olivia. Yeah, I like what Samantha said. If that's what you meant, that's cool. I'm not quite sure what you meant, Olivia. I'm sure it was good. So right, so we would make that. Then it's not clear if this is. Oh, chart mean E1, E2, SN1 E. Okay, yeah. Okay, if you meant that, then yes, we can definitely do that. Sure, yeah, no, absolutely. If this works for you, please do it. If it doesn't, ignore it. You're never going to get marks for it. I don't care. It's just to help keep your logic straight. Yeah, absolutely, Olivia. I see exactly what you mean. I'm very sorry. I don't think of it that way as a chart. I don't know what I think of it as. So now that we've done that, can we rule anything in or rule anything out? Can we rule anything out? Are any of the E1, E2, SN1, SN2 impossible under these conditions? We have to go a little faster than that. Yeah, the eliminations favor heat. So what things are favored, but is anything ruled out? Is anything impossible? Not. So Emily's saying not E2 or SN2 because it's acidic. So Emily, I'm going to be a little modify that. I'm going to say that they are possible. They are not impossible under these conditions, but I agree that they are unlikely. So let's just differentiate a little bit between things that are, I'll turn my camera because I'm staring intently at it and it makes no sense without that. So let's make a difference between things that are impossible, like cannot happen, versus things that are less likely than other things. So in this case, the E2 and the SN2 are not ruled out. They're not impossible. You're saying they're unlikely. I agree with you 100%. You're right. But they're not impossible. I think the only thing we can rule out is we definitely don't have a Hoffman elimination because we don't have a big base. It's a nice small stick-like thing. It's ethanol. That's what we got. Is it weak base though, Alyssa? Is this a base? Is this basic? There's H plus. I agree with Emily that's acidic. Yeah, okay, there, never mind. Yeah, awesome. Okay, so we're acidic. Sweet. We probably should be kind of aiming towards the E1 and the SN1. I'm with Emily completely on that one. I'm with Madeline especially on looking at the E1 because of the heat. I'm going to be a little cautious about whether heat really favors eliminations that much over the substitutions. But as I said, we're going to discuss why in this case here. So, and I think we're favoring the formation of a carbocation because of the acidic conditions. But again, for that to be possible, we need to be able to make a stable carbocation. If the carbocation is not stable, it doesn't matter how acidic your conditions are. You're putting this into like pure H+, and if you don't have a stable carbocation, it's not going to do an E1 or an SN1 because it can't make a stable carbocation. So we can look at what we get. If we're going to make a carbocation, the leaving group leaves. And we get that as a carbocation. Is that a stable carbocation? Yeah, so Alyssa, you're so just while everyone's thinking about whether it's stable, Alyssa, you were looking at the ethanol. Just look at the overall conditions over whether, like, you're right. Ethanol is a weak base, but we're under acidic conditions because we added H+. So Alyssa, yes, we have resonance, right? So there's resonance, so it's a nice stable carbocation. Okay, so we've got a good carbocation. We've got nice acidic conditions. Really, we're looking at that E1 SN1. Now, if we're trying to figure out if it does an E1 or an SN1, we probably want to look at the size of the nucleophile and the size of the electrophile. It's a small nucleophile. There is no particular steric hindrance on the electrophile. It's a nice, easily accessible secondary carbocation. So SN1 is looking good. Exactly, Megan. My phone is catching up and letting me know that you're all here. So Megan said, so even if we were under acidic conditions, we didn't have a good carbocation, we would consider SN2 and E2? Yes. Because if you can't make a good carbocation, you can't do SN1 and E1. And so that leaves you with SN2 and E2. You need to make the carbocation and do SN1 and E1. Anyways, we've got a good carbocation. We have a small nucleophile. We have a small unhindered electrophile. The SN1 is looking good. The SN1 would react at the center with the most positive charge, which will be the secondary, not the primary. So you look at both resonance structures. We generate that product. And then that's going to be in equilibrium with the deprotonated version. Okay, it looks pretty simple. We're missing something here though. And that's because we are under strongly acidic conditions. This is actually back in equilibrium with the carbocation, because how is that what I've just drawn there all that different from this? The two things I circled in blue there are pretty much functionally similar, right? Like we have an alcohol, we have an ester, or ether. They're both kind of the same kind of oxygen. They're both protonated. The alcohol left. Nothing stopping the ethanol leaving. The water left. Nothing stopping ethanol leaving. Like, yes, Le Chatelier's principle is going to favor that SN1. We have a second thing happening here, and that's that if we consider the E1 reaction, we're going to get a molecule with two double bonds. So Alyssa asked, why does Le Chatelier favor the SN1? We have an awful lot of ethanol. It favors going forward, I guess. So we have an awful lot of ethanol. We don't have any water. So we're trading water for ethanol. Like we're releasing water and putting ethanol on. So it does favor this over the starting material under these conditions, because you just have a lot more ethanol. So it's much more likely to be on the molecule than the water is, because there's not a lot of water. But this is all complicated, because everything is, by the fact that under this heat, the nucleophile coming in and coming off is reversible. And if we generate the carbocation, we can do the E2 or E1. And now we have the double bonds in resonance with each other. So we see that heat favors the elimination, because elimination is harder to reverse. Nucleophilic substitution can become an elimination. Eliminations have a harder time becoming nucleophilic substitution. Yeah. So I would think the answer to this question is that. Now, if there was no heat, I'd have favored the SN1. If you answer either, you get the mark, because they're both going to happen. And if I say draw all reasonable potential products of this reaction, I would expect you to draw both the SN1 and the E1 for this, because they're both completely rational choices. It does depend on the specific circumstances, and you're probably going to get both no matter what you do. The reason you get both and it's a mess is why nobody uses SN1 reactions to do anything, because you lose control of the situation so easily. Emily, I am happy with that answer. So Emily says if there's heat and it's between SN1 and E1, it will always be E1. Yeah, I'm okay with that. If the nucleophile is remotely basic. If you have a really not a basic thingy, then it's going to favor the nucleophile, but I can't think of many examples. Okay, let's try a different one. So let's think about this. So you have to identify the reaction and then draw the mechanism for this transformation and give me the product. Any suggestions? Yeah, we can eliminate Hoffman. I completely agree. We don't have a bulky base. Okay, so Liz says like is basic conditions, and she's right. So we can eliminate the SN1 or the E1. Can't make a carbocation under basic conditions, just not competitive. Basic so favors SN2 or E2. Yeah, as in saying we can eliminate the SN1. Malit says like, okay, take off a hydrogen and form a ring. Okay, so you're on the right track there. So again, and I keep pointing this out, and I think I pointed out again off hours. I'll have to post those. You can actually access all the recordings, I think, under the class notes, but I'll try and post them to YouTube anyways. I keep mentioning the fastest reactions are acid-base reactions, and intramolecular reactions are faster than intermolecular reactions. If you can make 5, 6, or sort of 7-membered rings, definitely 5 and 6, 7 to a lesser degree. Because I thought that was E1. Totally meant to do that. Okay, so are either of those OHs easier to remove than the other one? Because you got 2 OHs on this molecule. Yeah, right. They're both the same. They're both more or less identical. Okay. So next question I've got for you. If I remove one, let's say I did this. Do you think that's fast? Like if I remove one, can I take the other one out very quickly? Like they can switch. I'm going to take performance enhancing caffeine. Lauren's saying it's not fast. Well, they're about the same, but this is very fast. This occurs fast. So this can switch back and forwards like crazy fast. And it's because maybe it's using the ethanol solvent to participate that, but any acid-base reaction is very, very, very fast. Moving hydrogens around is basically instantaneous. So when do you do intra versus inter? It depends what the reaction is. Acid-base reactions are fast. I don't know how many more times to say that. They're fast. They're very fast. Acid-base reactions are fast. Fast are acid-base reactions. This is an acid-base reaction. It is fast. So what other kind of chemistry can we have going on here? Well, we could have eliminations, or we could have substitutions. Eliminations are often very competitive because the substitution needs to navigate a rather difficult angle of orientation, right? The cat door thing. But when the pieces are tied together, like they are here, the substitutions become pretty easy because there's only so many ways the molecules can approach each other. You have a limited number of degrees of freedom, and it becomes a whole lot easier for molecules to close in on each other when they're attached. So suddenly substitutions are very fast intramolecular. They're so good actually that you can do SN2s on tertiary centers if you have an intramolecular SN2. I'm not going to trick you with that. We're going to leave SN2s with tertiary. It's just a thing that doesn't happen, but it actually can happen if it's intramolecular. So this is going to be the acid-base reaction is fast. That is intermolecular. But now eliminations or substitutions will be intramolecular and they will be faster. So the question I've got then is which of these reacts to make the ring? The right-hand oxygen or the left-hand oxygen? And are they if they're the same, that doesn't matter. But if they're different, then it does. The products are different. We have one vote for left. So if that did that, it would do that. To make a 6-membered ring. Don't have that. The placement of the eye is very important. Okay, so Samantha said the 6-member ring is better than a 5-member ring, so the left product. Okay, perfect. So you're all thinking fine. You're thinking, hey, 6 is more stable than 5. You're all absolutely right. 6 is more stable than 5, but is 6 faster than 5? Because we have perfect, Melitza. Because 6 is if things can interconvert, if this can now go backwards, if this was all in equilibrium, the 6 would dominate. But is it in equilibrium? Once I make that, is that going to go back to, is the I minus going to come in and kick out the oxygen and put us back to where we were. Because I minus is going to displace O minus. No, it's a horrible trade, right? O minus is, that's not the worst thing in the world, but I minus is pretty stable. It's great. So this isn't reversible. So once you do the ring closing, that's it. Can't go back. So stability is really important. And all of you are thinking about stability, and that's great. I applaud you. That's awesome. You got that. It's cool. It's faster. 5 is faster. 5 is the fastest. Not the best, but we're not looking for the best. So 5 rings are less stable than 6. But they form faster. Yeah, so speed dominates if there's no equilibrium. If there's equilibrium, then stability dominates. This is kinetics and thermodynamics. So let's talk briefly about that. So we have our starting material. And well, let's say we have the 2 starting materials. We've got O minus 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, this is hard. 1, 2, 3, 1, 2, 3, 4. So we have that. We've got this. This is a reaction coordinate diagram I'm drawing here. Energy. They're about the same energy. We agreed on that. O minus on the left, O minus on the right is about the same. And they interconvert through some energy barrier. Because you have to deprotonate one and protonate the other. This one then goes to the product with the 5. Perfect. And this one goes to the product with 6. Now, I'm exaggerating differences here just to make a point. Differences in energy aren't that big. So what we notice here then is if we follow the red pathway, this barrier is smaller than that barrier. It's going to be easier to get over this red pathway if I'm a molecule. The red pathway is faster, but the product is less stable. Whereas the green pathway is slower, there's a bigger bump, but the product is more stable, lower in energy. So the question we've got is, once you make this product here, can it go back? Because if this can revert, then everything is going to end up down here because that's the most stable point on the entire diagram. And molecules are lazy; they can go to the most stable thing. But if you're trapped, if once you make this, you're trapped, then everything is going to end up here. So these are reactions. These are called under kinetic control. And this product here would be under thermodynamic control. And this is actually really the same thing we just saw with the SN1 E1 thing with that double bond. And I was saying, look, if it's cold, you're going to favor the SN1. And that's because you have the kinetic control. You add the ethanol, it's harder to take it off and go back. But if it's hot, you go for the most stable thing overall, which was the diene product that we had, the E1 product. And so again, we have kinetic versus thermodynamic control. If the reaction had heat, would the six-membered ring be favored? Oh, very possibly. Yes, I'm short one carbon. Thank you. Good job, Melissa. Found a mistake. Melissa and Faith are really leading on the whole mistake finding thing. Yeah, you did this in the lab. This is it in reality. This is what's going on. For SN2, don't we need an aprotic solvent though? You don't need one, it helps. But when it's intramolecular like this, good luck stopping it doing an SN2. You really can't. Okay. There's almost like a wall actually between a lab and a course. I don't actually know what the labs are. We talked about them ahead of time, but now I forget because we talked about them last year before we did them when we were designing them. I want to do another example now. Very similar example. The DMF is solvent. Again, we're going to run this one really cold. Well, not really cold, but 0 degrees. We wouldn't heat it. Can I repeat what I said about speed dominating stability in terms of equilibrium? When you have an equilibrium, stability dominates. That's what equilibrium means. When you don't have an equilibrium, when a reaction is irreversible, speed dominates because it's irreversible. An equilibrium means that things are reversible. Like that's what equilibrium is stuff goes back and forth until it finds a balance. But if it's not reversible, you're not looking for a balance, you're looking for what's fastest. Order for speed for rings, Melitza, is 5 is faster than 6, is faster than 7, is faster than 8, is faster than 4, is faster than 9. And at this point, 7 is a lot faster than 8. It really starts slowing down. 5, 6, and 7 are quite easy. After that, it gets hard. 3 is a bit weird. Because 3 is really, really unstable, but forms really quite fast because nothing can move. I'm not going to put 3 in that to the chart. So 3 is often faster than 5, but normally it's very temporary. We saw 3 with the iodoniums and the bromoniums when we were doing double bond stuff. They were adding I plus and Br plus, and 3 was just fast. Like it automatically did 3. Okay. What do we think about this example? We're going to get a ring. Do we get a ring with sulfur in it, or do we get a ring with an oxygen in it? So Madison's on team sulfur. Want negative on most electronegatives, so ring with oxygen. Jesse's also with the oxygen. So Jesse's with oxygen because they make the 5. Jeanette's with the sulfur. So we have a 2-2 tie with, I don't know, 50 people in the room. Brendan's on sulfur. Want a few more. Just think this through. Because you can see why this gets so fucking complicated, right? Like this is an easy question. Really simple question. There's 2 things in there. Okay. So it's because we need to think about all these things. So what happens first is the acid-base reaction. And what's more stable? In the last case, we had 2 O's. They were about the same stability. Here, we want to have the H removed from the sulfur because S- is more stable than O- because S- is bigger than O-. S is bigger than O. Exactly. So perfect. So that those of you who are coming with the oxygen thinking, okay, more electronegative, that's right. It is more electronegative. Just remember that S stabilizes negative charges better than oxygen. Going back to the very beginning of the course, right? Basically, I'm asking one of those questions right up front. Here's the equilibrium. Which way does it lie? And we're going to deprotonate the S. And in this case, yes, there's an equilibrium where it can also deprotonate the oxygen, but the charge is mostly going to be on the S because the S is more stable. So although this is going to make a 6-membered ring, which doesn't form as fast as a 5, the negative is on the sulfur, not on the oxygen, because it's a sulfur, non-oxygen. So we're trying to figure out where the charge is to make it. So the last time we had an equal race, the 2 oxygens were identical, and it was just 6 versus 5. Here it's not equal. The sulfur is going to have the charge. The sulfur is the one that makes the bond. No, we have the same issue with it's always intra if you can, I think is maybe the way to think about it. Fuck. I was really careful too. I really thought about 1, 2, 3, and then I just. Wow, bugger this. Okay. I'm calm. It's okay. So yeah, that's what happens there. Madeline, by the way, I love the avatar of your cat. I don't know if it's your cat. If it's not, the cat trying to get out. I think that just encompasses the second year experience. And so I really appreciate your picture. Nice. You good? Yeah, it's not a safe place to go. Okay. Hey, counting atoms is half the battle. As you can tell, it's not one of my strengths. Trying to think of a good case here. Anyone have one of the a comparison they want to be thinking about? Oh, you know what? Here. Let's think about this. So if I have one equivalent of sodium cyanide, I made this problem more complicated than it needed to be, but you know, it's part of the whole game. What am I going to do? Like type of reaction and which leaving group am I going to displace? Let's run through a few examples with this kind of pattern. I as leaving group is charge better, absolutely. What kind of reaction am I going to do though? Substitution I because better leaving group. What kind of substitution? I agree it's a substitution. Cyanide is one of these stick nucleophiles. It's a shitty ass base. It's a good nucleophile. Yep. So I'm just looking for somebody to use them. There we go. Thank you, Madison, for putting me out of my misery. Okay, it's gonna be an SN2. Perfect. Awesome. Okay, next example. One equivalent of sodium cyanide. This guy. We do inversion, but notice that this is not, I haven't drawn any stereochemistry, and this isn't a stereo center. There's two hydrogens here, and I didn't indicate any stereochemistry. So it is inverting, it's just we can't tell. Yeah. Okay, so this new example. Same question. Basically, what type of reaction and what's the leaving group, just so we can kind of use this as a short form. Jesse's like SN1 or E1. I don't think so. Yeah, chloride's leaving group now. Yeah, so chloride's leaving group because we're still under basic-ish conditions. And so this kind of comes down to SN2s and E2s are generally faster than SN1s and E1s when you have a charge, because the cyanide is negatively charged to begin with. The charged thing wants to react. It doesn't want to be negative. Cyanide doesn't want to be negative, it wants to be neutral. To get an SN1 or an E1 to happen, you need to take something that is neutral and make it charged. That's bad. To get an SN2 or an E2 to happen, You need to take something that's charged and make it neutral. That's good, right? Like the cyanide is going to become better. So you pay less of a cost for SN2 and E2. So if something is charged and reactive, the SN2 and E2 are fast. So I agree with those of you who are coming down on the side that we are just going to displace the chloride. It doesn't matter that the iodide is a great leaving group. We're favoring SN2 chemistry here. Okay, another example. What do you think of them apples? Okay, what do we got? So this comes down to, is cyanide basic? So in a previous example, the chlorine leaves because we're favoring SN2 reactions. The SN2 is possible with the chlorine carbon. It's not possible with the iodine carbon because the iodine carbon is tertiary. Well, in this case, the iodine and chlorine are about the same level of hindered. I'd actually argue the iodine is maybe slightly less hindered because the chlorine is right next to the carbon. Yeah. So Faith is right. Cyanide is not basic. It's a good nucleophile. So we're looking at those and going, hopefully we're looking at those going, I don't know. They are both tertiary. I don't like tertiary. It's a nucleophile. It's not a base, but they're both tertiary. I don't like tertiary, but it's a nucleophile, but they're tertiary and I don't like tertiary. Why are we favoring SN2 over E2 in a previous example? Because cyanide's a shitty base. Cyanide doesn't do E2s. I think I say in one of the lectures, cyanide and azide do not do E2s. They just don't. They suck. They're not basic. They're not going to take away a hydrogen. So I'm going to stand by this statement saying they are not basic. They are not going to take away a hydrogen. So what has to be happening in this third example? Right, SN1, because the SN2 is not possible. As I said, the SN2 is faster than the SN1. The reason SN2 happens under basic conditions isn't because the SN1s are impossible under basic conditions. We say they are, and it's because they are so fucking slow. You have to make a carbocation that is slow. SN2 is like a missile. It's fast. Charged thing, doesn't want to be charged. Boom, bam, explosions. The SN1 takes time. You need to, leaving group needs to leave. It doesn't want to leave because it doesn't want to be charged. So it slowly wanders off. And then nucleophile comes in. The SN2 is going to win every time because it's faster. But no SN2 is possible. E2 is not really possible because cyanide is not a base. So that gives time for the SN1 to occur. And of course, we are going to have the iodide leave because it is the better leaving group. The carbocations are the same. Iodide's better leaving group, and cyanide comes in. Or rather, the SN2 is inconceivable. Recently rewatched The Princess Bride. Do that about every 6 months. because that probably should be done. Okay, so I think that we've talked about a lot of the fine points on these things and the way that we need to consider freaking everything. If you're given a question and you're asked, how is this going? You need to look at these different options. I promise there will not be a question on the there are definitely questions on the assignments which are full of gray areas, and I talk about that. There will not be a question on the final which is going to be gray unless I intend it to be gray, and I'm basically saying discuss the different possibilities here and why you would favor one over the other. And I might not even, I might just say draw potential answers. I might not even say draw the answer because it might not be clear. But so unless I'm asking a question for you to basically discuss the factors, and I'll openly sort of say that, then I'm not going to be asking you gray questions on the final. The problem is reality is mostly gray because that's the way it works. I don't consider any of these ones gray on this slide. There's only one thing that could really be feasible in any one of these cases. But those secondary leaving groups under acidic conditions that could do SN1 E1, SN2 E2s, it's all pretty similar. Yeah, those are tricky. I promise not to do that. Yeah, E1's not possible because cyanide's a crappy base. Yeah, it's going to be a nucleophile better. So it's not only is it a crappy base, it's also really small. So it's a really good nucleophile. It's like both a really good nucleophile and a really, really shitty base. So yeah, SN1. Okay. I think we're done. We'll be moving on to radicals for Friday. So watch the intro radical lecture. The radical stuff is both hard. It's initially kind of challenging because it's a different way of thinking because everything we've done so far is ionic, but then it gets pretty simple. And so that's kind of the idea is that we have a little bit of a breather at the end of the course to try and catch up all this other stuff. I think what we've just covered is the hardest stuff in the course. Mechanistically, the most complicated mechanisms are things like the ozone and the sodium and the hydroboration, deboration. I think those are mechanistically the most complex mechanisms in the course. But I think conceptually trying to balance 4 different things, where any one of them can happen, is the hardest stuff in this course. Why is cyanide a bad base again? It is a bad base because the conjugate acid is very strong. HCN is a strong acid, a reasonably strong acid. And so it's not really favoring to take away the hydrogen. I think that's the best answer I've got. CN- is also pretty stable. So the 4th assignment is not going to be this week. The 4th assignment is going to be next week. I can't legally have an assignment due within 2 weeks of the final, but everyone asked to delay it, and it made sense because we delayed the last one. So what I'm saying is the assignment is due this week, 2 weeks before the final, but everyone's got a whole week's grace period, and technical issues are preventing us going to be loading it up on Thursday. So you're going to get that same 3-day period. It's just going to be next week. Just dancing. I think it actually makes sense because it gives you're going to be reviewing for this stuff anyways at that point. I bet you this is probably your first exam. It's really early in the exam period. Yeah, it opens next week. The assignment's going to open next week. It's not going to be available this week. I think I point that out in the assignment. The assignment is not going to be available this week because of technical issues. Technical issues being that we haven't written it yet. Okay. But it's going to kind of summarize some of the stuff. It's a good kind of review going into the exam. Oh God, you got to be fucking kidding me. You poor people. I'm so sorry, Julia. Yeah, this just sucks. Once this term is over, you'll never have a term this bad again. That's the only good thing I can say about it. This is the worst term in undergrad, and it's not actually all that close. Yeah. Yeah, I'll give you to the Sunday night. So it'll open up Thursday night, Thursday midnight, and it'll be due Sunday midnight. Yeah, you know what? There's a lot of stuff to learn in science in 4 years. That's what it comes down to. Okay, but I think calc is first year, maybe. So I'm not going to feel as guilty about that as I can't schedule for all of those, but still, that's going to be keep sane, drink lots of water, pat lots of kittens. I don't know. I'd say get lots of sleep, but we all know we're lying about that. So, okay, have a good day, everybody. See you later.